Ferrite rods, Litz wire. We're going past the magic of crystal radios and we're going to go right into alchemy now. This is the really wild stuff. Forget about those 130-foot long wires and those 15-foot ground rods. We're going to see what we can do right on the kitchen table with a simple ferrite rod front end for a crystal set.
I always get discounts and it's automatically done. It's never late, you know? And so I have a ton of people that have electronic access to mine. But I'm in an adversarial relationship with them.
Your hands are full. Somebody help me carry this stuff in? Our ears are open. Alexa, play WIBX 950.
America, we have a country to save.
Spit on and verbally... Why? Because they wear the blue MTA uniform. I'm Tony Utano, president of the Transport Workers Union, Local 100. No other workforce in New York City has to deal with this type of disgusting abuse and disrespect.
We're going to see what we can do with these ferrite rods by making a tuned radio frequency amp that's around this rod as the central antenna. Yes, I'm talking about tabletop reception. Forget that external antenna. Forget the 15-foot ground rod. We're going to attempt to pick up stations right in the kitchen. And I think you're going to enjoy this video. So I did want to go through some very simple applications of ferrite cores before we get into some of the more exotic stuff, the kitchen table, for instance. We can use it as a conventional coil. So what we are looking at here is a crystal set, a simple crystal set that's built around a ferrite rod sitting next to our original crystal set, which is it's got the wooden core. And when you've got about a 365 picofarad variable, in order to cover the broadcast band, you need around 240 or 250 microhenries of inductance. And we found with this coil that was about 100 turns. Now on the ferrite core, we need about half that number of turns to reach that same amount of inductance. So I think there's around 55 turns on this to cover approximately the same sweep. This particular crystal set is a 3-coil arrangement. It has a primary that looks like it's around 10 turns. It has a secondary that is tuned of 55 turns. And it has a second secondary that feeds the diode, and that is 20 turns center tapped. When we don't have a lot of signal, I tend to use the whole 20 turns into the diode. When we need some extra selectivity, I'm only using about half of the coil into the diode. So we have the crystal set hooked up without a tuner to the 130-foot inverted L.
Too, yeah.
Divorce, it could be any kind of a...
North's announcement comes during a time of...
we can't sermon, we can't even, feed and clothe on the homeless.
Okay, so it's acting about normal. That's about the same performance we had on the other crystal set. Now the ferrite rod that we're using in this crystal set is one of those manganese zinc rods that are very low cost. You see them on eBay and all over the net. They usually cost $2 or $3 each. And this particular type of ferrite is useful up to, probably 3 or 4 megahertz. It has a fairly high permeability, usually between 200 and 400. So it is not like the type 61 material which only has a permeability of around 125, which is more suitable all the way up to higher frequencies. But this low-cost mix is readily available, and you can get some very high Q inductors out of this stuff. So I decided to use this very low-cost material to show you a simple crystal set, and that the performance is very similar to what we achieved with our 1-inch or 1.5-inch solenoid style coil. We're listening to a Boston station using the little 40-foot inverted L with the tuner. Okay, so it's working very similarly. Let's see what we can do with a piece of ferrite as an antenna tuner. What are we looking at here? This little contraption is an antenna loading coil, but as you notice, it has a funny tuning mechanism. And let's see what we can do here. So instead of using a slider like we did with the wooden core loading coil, we're using a ferrite rod that's just been attached to this non-conductive rod. Could be a wooden dowel, or in this case it's a piece of fiberglass, and I've got it calibrated. Depending on what tap you attach to, I have it calibrated to tune the little 40-foot antenna. It actually is giving a little bit better performance. That's because, as you can see, the coil is made of much thicker wire, and it has less resistance, and it's doing a better job tuning the antenna. We know that an air core coil with a solenoid type wind, like we see here, and the wood is essentially similar to an air core type of solenoid wind. We have distributed capacitance along the windings, we have resistance in the wire, we have proximity to other items. All of these lower the quality factor of the inductor. The Q, or the quality factor of the inductor, is influenced by more than just the DC resistance of the coil. It's influenced by the distributed capacitance and the loading, of course, on the coil. Now, when you introduce an iron component, it's going to make the Q considerably worse, because the iron is going to disturb the field and concentrate it. But that effect is more than offset by the reduced resistance and the smaller number of turns required to hit the same inductance. So we are still able to achieve quite a high Q with the ferrite rod. Once we put some Litz wire on the ferrite rod, the Q starts to really come up to the point where it's equaling some of the air core type designs. So the magic of Litz wire versus ordinary enamel copper wire. I've got a nice form. This is type 61 ferrite. We're going to start by winding some ordinary enameled wire on it and resonating it with a capacitor. And we're going to be using the bandwidth method to try to measure the selectivity of the tuned circuit that we produce. And by using the 0.707 voltage points each side of resonance, we will determine the Q of the tuned circuit. Then we will replace this nice number 22 enameled wire with S175 46, which means there's 175 strands of number 46 wire, and this Litz wire is roughly the same diameter as the number 22. So using the same number of turns with the Litz wire, we will repeat our Q measurement and see if we're producing a better coil using the Litz wire. This is a little bit of a crude method we're going to use to measure Q, but frankly most of them are. So we'll try to use the generator along with the frequency counter and an RMS voltmeter. The generator, the frequency counter over here, and the RMS voltmeter, and we'll come up with a way to measure bandwidth. I have wound 55 turns of number 22 enameled, close wound, approximately in the middle of the core. Now we need to resonate that with a variable capacitor. Have you ever been given something and you wonder, when am I ever going to use that thing? Well, we've just reached that point. This is a general radio wave meter. And you would attach coils to this and it would resonate and would pull energy out of the circuit, and it would tell you what wavelength you're on. And it's calibrated in meters. Well, if you open this thing up, and I would estimate this is late 20s or early 30s type construction, you find out what you have inside is a very precise variable capacitor. Okay, let's look at our method of Q measurement. This is called the transmission method, and we use two small value capacitors to couple a signal into the tune circuit and out of the tune circuit into the RMS. We're going to do our testing at 1 megahertz. There we are, getting up there. This one and down here. Okay, that's about right. Okay, so we're set up to take the Q measurement, and we will come off frequency until we're 3 dB down. 1, 2, 3. Okay. So we moved about 5 kilohertz up, and now we go the other direction. So it's about 10 kilohertz of change that we're seeing here. Okay, so we've determined that this particular wind on the Type 61 core has a Q of around 103. So next we're going to remove the turns, and we're going to measure out Litz wire at the exact same length. We'll put it wire to wire to make sure we have the exact same length. And we're going to wind the Litz wire in the same position, and then we will attempt to measure the Q on the Litz wire. Got a couple pieces of suitable stranded hookup wire. It's not even Teflon wire, it's regular PVC wire, and I've stripped the ends. And we're going to attach that one of the pieces to the end of the Litz wire. I've got the stranded wire in the vise, and here's the Litz wire. The first thing we're going to do is unwind some of the sheath so that we can get some of this exposed. Okay, so I've done it, and look at all those strands. Isn't that amazing? Next we will clip the tag end off. Now each one of those strands, and we know we have 175 strands of number 46 wire. Now I want you to strip every single one of them one at a time using a pocket knife. No, I'm just kidding. Actually, all we're going to do is we're simply going to wrap them around the stranded wire just as is. Just wrap it right around. Done. Then we're going to take our well-tinned soldering tip and we're going to go in there and we are simply going to apply enough heat to the joint to get solder to flow and to melt through the insulation. Okay, and you'll see it bubble up. You know you're doing the job. And there we are. The bigger the blob, the better the job. Okay, then we're going to fold the hookup wire back along the Litz wire connection. And we're going to connect it into the place where we want to start the wind, just like so. And we're going to wrap that with tape. Okay, so we've got some tape on there now. We're ready to start our winding. So there's a million different ways to wind these things. The Litz wire is somewhat slippery. So I put it through a couple pieces of cardboard. I got a couple batteries on there for weight. I've taped them down. We don't want too much stress. But you do need to have some form of tension control to do this right. And we're just going to start winding. Now when we're just about there, this is a tricky part, it'd be a good idea to maybe tape this at this point. Do your connection with the hookup wire and then get back to it and finish off the wind. So I repeated the test a couple of times and found that maybe 140 is closer to the Q I'm getting with the Litz wire. It seems to be pessimistic, and I think most of these methods of measuring Q are somewhat pessimistic because you are loading the circuit and there are some proximity effects. So what I'd like to do now is simulate what it's like to have an antenna coupled into the rod. So I've got a 68 ohm resistor and 180 puff capacitor that represents the antenna. And the load, of course, the diode load, I simply have a 10-turn coil going into a 68K resistor. Let's see how that affects it. You might remember with the enameled wire we had about 103 for a Q, and by using the Litz wire we were able to bring the Q up to about 140. And now that we've loaded the circuit with the 68K and the simulated antenna of 68 ohms and a 180 puff cap, the Q has been reduced to 124, just about 125. So depending on how you load this this rod, both with the antenna connection and your impedance matching into the diode and to the headphone, you can ruin your selectivity. So that's why the Sirius crystal radio guys take so much time to get the impedance matching correct. They want to preserve the selectivity and the signal level. As you may remember, radio propagation consists of an electric field and a magnetic field that are perpendicular to each other. Wire antennas can receive either, and sometimes both, but are primarily sensitive to the electric, or E field, of the wavefront. Loop antennas are primarily sensitive to the magnetic, or B field, of the wavefront. They convert the magnetic part of the incident electromagnetic wave into an electrical signal that we can amplify and detect. That's what antennas are all about. A ferrite rod intercepts and concentrates the H field much more compared to just a plain wire loop antenna. In other words, more flux passes through the core than if the same geometry were air with no core. Of course, as the loop gets physically larger, in some geometry it will overtake the rod in signal reception. but in a small space at least, the rod does a fantastic job as an antenna in the broadcast band. Let's look at the rod materials. The early types of cores and rods were made of powdered iron. This could be mixed with a filler and nickel powder to affect the permeability and effectiveness of the mix over some frequency range. The entire low frequency to HF range was covered with powdered iron. And even today this material is utilized in miniature toroids all the way up to VHF. One early use of powdered iron was in tuning slugs. This approach was utilized in the groundbreaking design of the ARC-V transmitter's VFO and power amplifier slug-tuned inductors. What we find is that both the self-inductance and mutual inductance of a coil or transformer may be increased by inserting a slug of powdered iron inside the coil's tube. Inductance can be raised 2 to 4 times the value compared to the same form without a slug. This allows smaller diameter coils and fewer turns to produce higher inductances to be used at lower frequencies. Tuning a coil to a given frequency was at one time always done with variable capacitors or tapped coils. Now the inductance or tuning could be changed with a slug of powdered iron. Permeability-tuned intermediate frequency transformers, or IF transformers, begin to show up around the late 30s, mostly in the superhet receivers and in the low-level stages of transmitters. These powdered iron cores were useful in improving the stability and reliability, and of course in miniaturizing the IF and RF coils and transformers. Trimmers aren't that reliable. They get oxidized, hard to turn, and sometimes they short out. You can tell you are in possession of a powdered iron core or slug because they generally are a dull color and are softer and can be easily filed. Many times they will be covered with an epoxy paint to keep them harder on the outside for the windings and to increase the high voltage electrical insulation. Because of its low cost and soft saturation characteristics, powdered iron is still used in high frequency power supply inductors at least to around 1 MHz. Modern magnetic powder cores, such as those inside your PC power supply, are most commonly toroidal cores made from 90% iron powder, and they're specifically useful in switch mode power supply transformers, switch inductors, or chokes. More expensive mixes include nickel and molybdenum. Mix 26 is the most common, and it's found in switch mode power supplies. You can recognize these toroids because they're yellow or yellow and white in color. Some very old radios used wire loop antennas, and some powdered iron rods do show up as antennas in some of the older receivers, but there was a switch to ferrite rods which occurred by the mid-1950s. Let's talk about ferrite rods that we can get hold of today for our projects. The most common and inexpensive type is the manganese zinc MnZn type ferrite. This type is usable for broadcast band inductors, and it produces a good Q tune circuit up to around 2 or 3 MHz. Less common and more expensive are the nickel-zinc NiZn ferrites. This class is characterized by its high material resistivity, which is several orders of magnitude higher than the manganese-zinc ferrites. Nickel-zinc ferrite is the material of choice for operating from 1 MHz to several hundred MHz. Type 43 ferrite is one of those nickel-zinc ferrites, but it's of questionable use in the broadcast band as a high Q inductor for our antenna. Type 43's high in permeability at 850, and that makes it of limited use as a high Q inductor at the higher frequencies. Type 43 material is generally a lossy material above 1.5 MHz, making it an excellent choke or transformer material. That said, at least in small toroids, 43 material can be useful up to 10 MHz in high Q service. Type 61 ferrite is useful over the entire HF band as a high Q or even a low Q inductor, and thus it's the preferred mix for our work. Type 61 is what we want to be using. A large number of nickel-zinc materials have been developed. Certain nickel chemistries like type 61 contain cobalt, which can cause the core to be adversely changed by some types of stress, such as mechanical shock from dropping or from some grinding operations. Resulting changes after stress can include the increase of permeability and core loss, meaning the lowering of Q. These changes generally cannot be reversed. In some cases, a thermal anneal at high temperature can restore some of the initial properties. In other words, don't drop the rod. So in review, manganese zinc types, including Mix 33 with its permeability of 400 to 600, these are the low-cost Chinese rods. They're useful to 2 or 3 megahertz. And the nickel zinc types like 43 with a permeability of 850, that's great for chokes. But type 61 with a permeability of 125 is the most useful at higher frequencies. That's what we want to be using. And finally, one way to tell if you have powdered iron or ferrite rod or core is to look at them. Again, the powdered iron will be dull and the ferrite will be shiny. And lastly, all of the modern ferrites are considered ceramics. They're going to be hard to file, brittle, easy to chip, and they'll break if you drop them. So does a ferrite rod type situation fit more what you would like to try at home? Do you not have room for a full-sized antenna and ground system? This can get you in the game in both the long wave and the medium wave frequencies, and it's fun to play with these different mixes of ferrites and see what kind of Q you can achieve with the coils. Hope you've enjoyed this little expose on the ferrite rod style of loop antenna.